Our objective was to build a collapsible shopping cart with an envelope that was small enough to fit into a car's trunk or in-house storage department. Since our cart has removable crates, this makes transporting goods more convenient and shopping bags obsolete. The collapsible shopping cart is lightweight, allowing majority of consumers to handle and store away with no assistance.
In our kinematic analysis, we applied graphical synthesis in order to create our collapsible shopping cart. This resulted in a 4-bar linkage with an equilateral triangle. Our ground link is our frame, link 1, our second link is our input link, and our coupler and output link formed a toggle so that our mechanism could collapse freely. During calculations, it was realized that our mechanism is a special case crash-off. As a result, the toggle position causes unpredictability as the mechanism can be assumed in two configurations. In order to reduce the motion of the configuration to collapse inwards, a brace will be installed at the node between the coupler and the output link to restrict the movement to the outward configuration. In addition, we apply position analysis in order to solve for our unknown variables, the coupler angle and the output angle. Using a vector loop as well as Euler equivalence, we successfully related our input angle to the unknown angles θ2 and θ3. Upon analyzing the positions, it was determined that θ2 and θ3 range from 120 to 180 degrees and 120 to 0 degrees respectively. Overall, our analysis allowed us to fulfill our desired mechanism as well as kinematically predict the behavior of our unknown angles.
In regards to force analysis, it was determined that it was crucial to calculate the pin forces of the shopping cart's linkage when the consumer pushes downwards on the handles to collapse it. Since the open position is secured by the toggle lock, it was found favorable to apply the force analysis at a 5-degree offset of the input link while it's still in motion. To set our parameters, we set the angular velocity of link 2 to be a reasonable 55 degrees per 3 seconds. The variables were found utilizing the following formulas. Next, the free body diagrams of each link were drawn with relevant pin joint force components. Then, the equations of motion is then formulated after calculating the linear acceleration components. This resulted in 9 equations with 9 variables. This allows us to convert the equation into a standard matrix form and apply the method of inversion. Conclusively, the vertical applied force was found at 0.107 pound force downwards.
We chose link 2 for a stress analysis because it was long and hollow. This made it a suitable candidate for buckling, normal, and bearing stress. At first, we chose our shopping cart to be made out of steel alloy, but soon discovered that the smallest safety factor was 30. This was too high for a shopping cart and indicated either the material was unnecessarily strong or the cross-sectional area was too big. Next, we chose aluminum, which dropped the safety factor to 13.5. And finally, ABS plastic, which dropped it dramatically to a 2.1. In all cases, the smallest safety factor was caused by bearing stress because of the thin walls of the link. Overall, switching to ABS plastic reduced the weight of link 2 by 66% while maintaining a decent safety factor for a shopping cart.